So this is the circuit diagram of a crystal oscillator. In this video, I'll explain the operation of the crystal oscillator. In the oscillators, we've studied till now LC oscillator, RC oscillator. In LC oscillator, two types we studied, Hartley oscillator and Colpitts. In RC oscillator, again two types, phase shift and Wien bridge. Now this is a different third type of oscillator called as crystal oscillator. In the previous video where I explained about the crystal, I have explained what is series resonance and parallel resonance. I would like to mention here again that whenever a crystal is in parallel resonance, it acts as an inductor. It gets the inductor properties. So we are using that property of the crystal here. See, if you can see the circuit diagram is very similar to the Hartley oscillator. It has got an amplifier, a transistor amplifier with its voltage divider bias, and in the feedback circuit we have a crystal which is in parallel resonance instead of the inductor. In the Hartley oscillator, you know that there is an inductor and two capacitors, correct? One inductor and two capacitors are used in the feedback network in Hartley oscillator. Instead of the inductor, what we have done here, we have used the crystal which is at parallel resonance. So it acts as an inductor, right, in its place. That is the only difference. So what happens when you apply this plus VCC voltage here, that EMF is applied across the ends of this crystal. So because of piezoelectric effect, it vibrates and oscillations will be set up. And A into beta is said to be 1, and this is giving 180 degree phase shift because a CE amplifier, and this also is giving 180 degree phase shift feedback network. So the closed loop phase shift will be 360 degree. So both of the Barkhausen criteria will be set and sustained oscillations will be created. Using crystal oscillator, we can have very high frequency, very accurate oscillations can be set up.